Okay, so the data set for this class, okay, is going to be digits data, and I'm showing you some digits data here. 65473. We have no problem recognizing the digits. Okay. Each digit that we're going to be faced with is a 16 by 16, grayscale image, and you might want the digits. I mean, such a boring solved problem. Yes, okay. But we need something that's within the scope of this class. Okay. But I'm going to go back to now the very first lecture. Okay. And I said we're going to be discussing the fundamental theory of machine learning, the fundamental algorithms, the fundamental techniques. Okay. And so, that means that once you have understood those fundamentals, they can be adapted to solve any problem. Okay. And so you illustrate on this problem, and you'll get familiar with the techniques and the theory. Okay. On this problem, it has all the richness of pretty much any problem, and then you can apply those techniques wherever you want. Okay. So that's sort of the generality of what we have developed so far. Okay. So I'll just mention to you some of the important things that go on when you start approaching the data. Even though I said that the theory that we're going to be developing is not focusing on the data, it's focusing on what you do after you get the data. So here's the data, and you might wonder, well, how did I get this data? It looks so nice. Are digits really that nice? No, and that's because there have been some vision algorithms. So these are purely input pre-processing algorithms that have been run that have nothing to do with the learning. And what they have done, for example, is they have rotated each image so that its axis is vertical. Just a simplification. It's a simple vision algorithm you can run. You will also notice that each digit, in some sense, fills the whole square. Okay, so there's been some rotation applied to make things vertical, and there has been some scaling applied so that the digits each fill the whole square. More precisely, either the length is the height of the box or the width is the width of the box. Okay. And in some cases both. So what this just makes learning later on a little bit easier, because the input examples are all sort of what we call input pre-processed or normalized. Okay. Now, we're not going to discuss such algorithms, but these kinds of considerations are very, very important. Okay. And it's how do you sort of get the data into the form that then becomes suitable for the machine learning. And then once you get the data, that's where the theory that we have developed begins to roll. Okay. So here's an example of the data. Let's get into a little more detail. Okay. So for example, the 6. Okay, what is it? It contains 256 numbers. So it's a grayscale image. Okay, where -1 is basically white, and +1 is basically black. Okay, so you have 256 pixels, and if you ran a perceptron on these 256 pixels, well, let's see. Okay, the dimension d is equal to 256. Now the augmented vector has 257 dimensions. Okay, and so if you run a linear model with this input, the VC dimension, dVC, is equal to, is d plus 1, so 257. And so the rule of thumb says that you need about, let's say 3,000, 10 times this. Okay, or if you want to be save 100 times this. So let's say you need about, 25K data points to get E in approximately equal to E out. Okay, and we are going to be trying to learn how to classify digits with far fewer than 25,000. Even 10 times that is 2,500. We're going to be trying to learn with 500 data points. So this is just, with 500 data points, you're just not going to have E in close to E out. So that's a disaster. Okay? So when we approach this problem, we have to say, well, we have 500 data points. So what kind of VC dimension can we deal with? We can deal with a VC dimension of about 5, of that order. So we want dVC approximately 5 or less, okay, in order to solve this problem. Because we need to establish the first step of learning. Okay, now, how are we going to accomplish that and simultaneously be able to get E in close to 0? And that's where what I'm going to discuss now is so fundamental, so absolutely important. It's this notion of features or feature construction. So feature construction. Okay, or how to get E in approximately 0 with such a small dvc. Okay? And if you look at the dictionary definition of the word feature, it's sort of something conspicuous, something that's distinctive, something that identifies an object. Okay? And so when you think about the digit classification task, and now this is before you look at data. Let me emphasize, we are doing all this stuff before we look at data. You understand, now I'm going to just illustrate by showing you on the data, but all of what I'm saying has to be done before you look at the data. So, for example, the top left pixel is white, and it's going to be white for pretty much any digit. So putting it in as a dimension on which you're going to build your machine learning model, it's just a dimension that doesn't vary, but it's going to affect your input dimension and your VC dimension and then your error bar, and it's going to lead you to conclude that you didn't learn. Okay? So there's a lot of redundant information in the data, but there's also a lot of useless information in the data. Okay? And so what we can do is we can try to summarize the input in terms of features that are going to be useful for classifying the digits. Okay? So summarize the input into features that are useful for classifying digits. Now I want to emphasize that this does two things. What are the two things it does? The first thing it does is it can reduce the dimension significantly, so it will reduce DVC for the linear model significantly, which means that we will get control of the error bar. So that's the first thing it does. And then you might wonder, but well, then we might, affect our ability to, get E in small, and that's where we highlight the word useful. Okay? And so this is where you sit down with the digits expert or the medical expert, and you sit down and say, okay, great. Now you are collecting this kind of data. Now what are the features that are going to be useful? Okay, and so you think about this problem in some abstract sense, and you try to figure it out. Okay, and you sit down and try to figure it out. Okay, and in doing this, you are increasing the chances. You're embedding into the feature only what is important. Okay, and that's a hard task. Okay, but that's the task you have to do to solve a machine learning problem well. You have to think about what are the characteristics of the input that I need, and they may be measured, they may not be measured. You can tell your client, maybe go and measure those things. Okay, and when you do that, you will find that once you have constructed the right features, the linear model will solve your problem beautifully, because the linear model comes along and controls E in versus E out. Okay? And that's what I meant when I said that if you cannot solve the problem with a linear model, you haven't thought about the problem. If any problem can be solved with a linear model, as long as you think about the problem and think about what are the right features. So for the digits, let's think about what are the right features. Okay, so now we're not looking at the data. So I'm closing my eyes. I'm not looking at the data. Okay, and I'm thinking, well, my task is to, let's say, classify a 1 from, let's say, a 0 or an 8, or let's say a 5. Okay. And if you think about this problem, now look, this is not data. I've just drawn this. Remember, my eyes are closed. Okay. And so I'm looking at this and I'm saying, well, the 1 has a few black pixels. So you could add up the number of black pixels. Okay. Let's call that intensity. Okay. And the 5 certainly has more black pixels. Okay, so this will have a high intensity, this will have a low intensity. So I expect intensity to be a good way to distinguish certain digits written down from others. Now, this is just from my knowledge of the problem, not from my knowledge of the data. Okay, that's key. Okay. What's another distinguishing feature? Some kind of symmetry. Okay. So think about it. Well, if I rotate the 1, it comes back to itself. Okay. Whereas the 5, if I rotate it, it's totally different. Okay. So, and think about other digits like the 0. Oh, lots of symmetry. You can rotate even a quarter turn, and it'll more or less be itself. Okay, so symmetry. Okay, so now I'm thinking about features, and let's stop there. You can come up with your own features, and in fact, on one of the assignments, you will be asked to come up with your own features. Okay, but all I'm doing here is thinking about what I know about this problem and what features would likely be able to distinguish between the two in the various different classes. Okay. So this is the first step, and now I need to convert these definitions or features into mathematical definitions. Okay? And then I need to be able to implement those in some kind of an algorithm, some kind of a program that takes an input and immediately converts it into these two, let's say, features. Okay? And basically what I'm going to do is I'm going to transform my data from this 256-dimensional data into, let's say, 2-dimensional data, okay, where my 2 dimensions capture intensity and symmetry. Okay? So this takes my data from 256 down to 2 dimensions. But look, the VC dimension is just now 3. DVC is equal to 3. So, because I'm using the linear model, and that's why the linear model is so powerful, it automatically takes care of the first step, providing you have a small dimension. And now you need to take care of the second step by thinking about what are the right features. Okay? So, let me show you this data. Okay? But instead of the 256 dimensions of, grayscale values, which, don't really make sense to a human from the perspective of separating out, from the perspective of distinguishing digits. Here are the data now plotted, just like age and income, but now I have intensity and symmetry. Beautiful now. You see, if I put a line somewhere like this or maybe like that, there are many ways now to separate this problem. I'm showing the digits 1 versus 5. So imagine that we simplified our task to only distinguish between 1s and 5s for the moment. Because there's this famous mathematician who said, you're approaching a problem. It's a difficult problem. Okay. The odds are, if you've come to a difficult problem that you cannot solve, the odds are there's a simpler problem you cannot solve. Okay. So let's try to solve simple problems. Okay. Because we have no hope at difficult problems otherwise. Okay. So look at this. The ones have low intensity, high symmetry. Now we're looking at the data. You're not allowed to do this. Because I'm trying to teach you what's going on. So I have to show you the data. But in practice, you can't look at the data. I just want to show you that when we went into these two features, look how beautiful it is. And you could separate with a line. Okay? The linear model solves this problem almost beautifully. Okay? You don't need sophisticated this and that and this and that if you sat down and thought about the features. Okay? Now I want to show you something else about data. And, if you think you're ever going to get data that's perfect and clean, think again. So let me show you some things in this data, and you might wonder, what? So, the line would almost get this perfect, except for some strange data point. So there's this guy here, okay, this blue circle here, which seems to have a high intensity, not much symmetry. Well, when you actually look at that data point, it's this one. You look at it and say, yeah, some people write ones like that. Most of the ones are nice and symmetric and not many black pixels. But some people choose to write their ones with this very fancy, big, asymmetric one. You should be taught in high school that you're not allowed to write ones like that, because didn't you know we're going to try to build a machine learning algorithm to distinguish ones from 5s? Okay? And then what's this? Well, it's classified as a 5. Okay? It's right over here. You're wondering, what is this thing that's a 5 with almost no intensity and a huge amount of symmetry? Now you might wonder, how am I measuring intensity and symmetry? Well, you have to come up with your own mathematical definitions. I came up with my own. You can come up with them. Figure out how to measure, intensity and symmetry. Intensity is easy. Just effectively count the number of black pixels. Symmetry is a little bit trickier. You have to come up with an algorithm to measure symmetry. And this thing is very symmetric, but it's a 5. I don't know who writes a 5 like that. Not me. Okay. But that's the data. You can't argue with the data. The data says that's a 5, and that's going to cause problems for machine learning. And you might think, you can now try to think to yourself, what if I used the most complicated model on the world and tried to make it so that were indeed classified as a 5? You'd have to contort and do this and that and so on and so forth. Okay, so you might think, what would happen there? Okay, but this is the data in my intensity symmetry features, and you see that data comes in all shapes and forms, and we have to be ready to deal with this, okay, in some sense. And, we are now ready to run our perceptron learning algorithm. So we have data in 2 dimensions. Let's run the perceptron learning algorithm and see what happens. Okay? It produces this classifier, which is okay. That's what it produced. Okay? That's what it produced after 1,000 iterations. It doesn't look that good. Okay? Okay, and what I'm showing here is, as you run the perceptron learning algorithm, the blue curve here is the in-sample error you observe. Okay, wild. And that's because the data is not separable. Whenever the data is not separable, the perceptron learning algorithm behaves very erratically. So you might think, imagine if I had stopped at 250 iterations, I would have got a beautiful in-sample error. Okay, but if I had stopped at 700 and let's say 705, I would get a bad in-sample error. And I happened to stop at 1,000, and my in-sample error wasn't that great. Okay, that's the problem with the perceptron learning algorithm. Let's see what happens. Okay, now, one thing I want to point out. What is this red curve that's bouncing up and down, bouncing up and down, bouncing up and down? Okay, that's the out-of-sample error. You might think, how did I measure that? Well, we have our tricks, and what's going on here is I'm going to give you 500 data points to learn with, and we're going to keep a data set of size 10,000 or so, 5,000 or so. Think of those as 5,000 test points, which you will be tested on. Okay? So it's a measure of the out-of-sample error. I care about your performance on those test points. Okay? Look at how it's going up and down, also wild. But that's not the important point. Okay. The important point is look at how it goes up and down, up and down, up and down, up and down, nearly perfectly in sync with the blue E-in curve. And I'm going to ask you to pause the video and think about why. Why does the red curve go up and down almost perfectly in sync with the blue curve? Okay. So pause the video. And if you're coming back and you figured it out, great. Okay, you really understood the theory. Otherwise, if you're just here for the ride, that's the theory at work. Okay, because we have just 2 dimensions, so the VC dimension is 3, and you got this tight link between E-in and E-out. That's the theory at work. That's why we do theory, because it works for us. Okay. So what this means is that your out-of-sample error will mimic what you see in sample. It'll go up and down according to the in-sample error. In other words, when you find a small in-sample error, it'll tell you that you have found a small out-of-sample error. This is, in some sense, the error bar. Okay, this height here, and then as E-in goes up and down, E-out goes up and down. That's the link that we worked so hard to establish theoretically. Okay, but this erratic behavior is because we're running the PLA. If we run the pocket algorithm, it very quickly comes to the minimum here and stays there. And look, it's a much better classifier. Okay, this guy's up here, this guy's down here. Okay, you might think, well, maybe I can tilt it a little, and probably if you ran for another 1,000,000 iterations, this is just 1,000 iterations, you'll probably do much better. Okay, so the difference between PLA and pocket. Okay. Let's talk about linear regression. So let me erase